Welcome back, everybody. This is our video solution to problem 10 from the fall 2020 Math 210 final. This problem is about using the definition of the Laplace transform to compute the Laplace transform of t, in fact, right? We want to find the Laplace transform of t and show that it equals 1 over s squared. Of course, we have a formula in our Laplace transform table that tells us that this is true, but it's very important not to just use the formula and instead to follow the directions, right? We want to use the definition. So, what is the definition of the Laplace transform of the function t? Well, it's an improper integral. We're going to let t go from 0 to infinity. We're going to take this function t and we're going to multiply it by a decaying exponential, which has this auxiliary constant s. So that's the definition. We just have to compute this integral. We see a couple things. First, this is an improper integral. Fine. Second, if we want to integrate this, we better use integration by parts. Just as an aside, we're seeing this quite a bit right now. People are trying to compute an antiderivative of t, e, and I don't matter if I even put the s or not, but what people are doing is they're writing, oh, look, I'll just break this up. Hey, doesn't that make life easier? Okay, well, this is a clever Carl move. Okay, clever Carl does this, and yeah, clever Carl's never right. Okay, this does not work. Not now, not ever. All right, this is just an incorrect thing. So we don't do this, okay? We're going to use integration by parts. Okay, we'll switch colors for integration by parts. So I'll give a name here. This can be our f prime of t. So f prime of t is going to be t e to the negative st. And I want to compute f of t. All right, well, let's break this up. I'll use my tabular method. I'll have t and e to the negative st. I take derivatives until I get to 0. I take antiderivatives. Because of this s, we have to think a little bit. T is the variable with respect to which we are anti-differentiating. So s is a constant. Okay? So it looks like it's a variable, but it's really just a constant for us when we anti-differentiate. Because it's multiplied by the t and I'm anti-differentiating, I have to divide by it. So we get negative 1 over s, e to the negative st. And when I anti-differentiate again, I'll get 1 over s squared. The negative goes away, e to the negative st. All right, draw our diagonal lines, plus and a minus. Okay, that means our f of t. Make a little room for it. Let's see. Each of these has an exponential, and in fact, I notice I have a minus in both, so I can pull out minus e to the negative st, and then I'll have t over s, and then I'll have a plus 1 over s squared. And so this Laplace transform is just going to be f of infinity minus f of 0. And so all I need to do is figure out what happens to this function as t goes to infinity and when t is equal to 0. Well, the equaling 0 is the easy part, right? I have a t, if that's a 0, I have an exponential with a 0 exponent, so that becomes a 1. There's a minus right there. Okay, fine, so it's a minus 1. This t becomes a 0, so that term goes away, and I just get a 1 over s squared. So I'll have minus 1 times 1 over s squared. So this f of 0 is going to be minus 1 over s squared. What about the f of infinity? Well, the short answer is it needs to be 0 because, okay, as t goes to infinity in this decaying exponential, the decaying exponential will go to 0. In fact, it'll go to 0 very, very fast. This piece over here is a polynomial in t, and as t goes to infinity, it will blow up to infinity, but not nearly as fast as the decaying exponential goes to 0. So this f of infinity is going to be going to 0. Now, if we wanted to prove this very, very rigorously, right, we would use L'Hopital's rule on this. All right, and when we use L'Hopital's rule and we take a derivative, this polynomial piece goes away. The decaying exponential does not. And that's why that limit will be 0. So in total, we have 0. Oops. We have 0 minus negative 1 over s squared, which is 1 over s squared. Okay, so again, this is, if you want, justified with L'Hopital's rule, or just our generic rule that decaying exponentials go to 0 faster than polynomials go to infinity.